Good morning, everyone, and welcome to this new online class of this week. I remind you that if you need more interactions with me or with your comrades, by the way, you can ask questions in our chat on talk.ecam.fr. Okay, so don't hesitate. Don't hesitate also to pause the video and maybe try to read around. And guess what should come next, or do anything that can help you be active during this viewing. Okay, so let's go. One of our important topics today is going to be about implicit functions, implicit function theorem, and also we're going to talk about some extension of this theorem to higher order spaces, which is called the local inverse theorem, and even we'll go to the global inverse theorem. Okay, this being said, what are we talking about? Um, well, we start with a function f of xy, a function of two variables, and we look at it as some specific isoline. That means we look at all the xy's that satisfy f of xy is equal to alpha. So that's a level curve, an isoline, whatever the name you want to give it. Okay, so the idea is that can we locally describe this isoline as a function y is equal to phi of x? And that phi is what is called that implicit function. So maybe let's do a bit of, let's try to represent this problem. So we have, well, in O3, so we have, let's say that this is x, y, and z. Let me draw a nice curve. So I'm going to take one that I can easily represent. Something like a downward looking parabola. Okay, so f of xy. Okay, that gives you the corresponding z. And let's say that if that's a downward looking parabola like this one, we can even give some equations for that. Z is going to be equal to, well, downward parabola would be like this. Okay, and if I don't add anything, that would be starting at 0. So let's say that's value a plus a. Okay, so that it's the top of this parabola is at level z is equal to a. Okay, so now let's choose some value alpha. Let's say that this is the corresponding alpha value that I'm choosing. And of course, it's going to correspond to some level line. Okay, so that level line is described by f of xy is equal to alpha. That level line corresponds to some values in xy. Okay, probably they're going to look like this. Okay, in the xy plane, anything that belongs to this green curve is going to be mapped as those points that belong to my isoline. So anything on my green curve is solving the equation of xy is equal to alpha. And the idea is that, well, let's say that you know some specific value, x0, y0, that belongs to this curve. So f of x0, y0 is equal to alpha. Can you describe the surrounding of x0, y0 that are going to belong to make the xy belong to that level curve? Can you describe it as maybe y depending on x, as y is equal to a function of x? So let's try it a bit. Let's view that the projection in the xy plane. Okay, so let's project this level curve. Okay, so what I'm looking for is all the xy's such that minus x2 plus y2 plus my capital A is equal to alpha. Okay, and of course, capital A is bigger than my alpha, so this is something like x2 plus y2 is equal to a minus alpha, and of course that's greater than 0, well, according to the drawing that I've done. And what do we have here? That's an equation of a circle. Okay, so you know that anything that is going to solve this is going to belong to my ugly circle that I've drawn, but that's the circle of radius, so centered in 0, but the radius is just going to be a square root of a minus alpha. Okay, and so anything that belongs to this circle, any xy that belongs to this circle is going to be mapped by the f function into one point of that level curve. Okay, so now the idea is that let's say you know, well, some x0, y0, so let's choose that one. Can you describe the curve around x0, y0? This curve, okay, maybe not the best color to choose. This curve around x0, y0, such that you know that you can express this as y as a function of x, okay? Well, in that case, it's pretty clear. Here, you can describe that upper part, and you can just write that y, well, we just solve the equation. If y squared is equal to a minus alpha minus x2, you can say that y is just going to be the square root of that, a minus alpha minus x2. Okay, and that describes the upper part of your curve. But you still need x to belong to minus square root. So in order to be able to write this, x must be between minus square root of a minus alpha and plus square root of a minus alpha. Okay, so take your time to understand that. But in that case, it's very direct. We can directly write y as a function of x. Okay, so we can write that y is equal to phi of x. Okay, and so for what then I can do is that anything that is going to be written, any points that are going to be written as x, phi of x, are going to solve my equation. So if I apply my function f to this is going to be equal to alpha. Okay, but that is for some specific values of x. Specific values of x. Okay, you see, because I could describe that light blue curve only for, I could only describe the upper part of this light blue curve. Okay, separately, I could describe the downward part of this light blue curve, of this circle. I could describe that part of the circle, but then I would need another function. I would need y is equal to minus square root of a minus alpha minus x2. Okay, and that would be y is equal to, let's say that's another function of phi 2 of x. So I would have my second implicit function such that if I take any couple of values, and x belongs to the same interval, so that if I take any couple of values described by x phi 2 of x, I am also going to be on my level curve. Okay, so that's in that case we could find explicitly the implicit function, right? But in some other cases it's going to be much harder, and what is going to be the idea is that we can approximate, we can first of all we can say whether it's happening or not. That's one point, and second point, that's just going to be locally. And finally, what we can do is, even if we can't have an explicit description as we did here with those phi and phi 2 functions, well, where we had this explicit formula for these functions, even if in some more complex examples, if we can't have this, we can have an idea of what it looks like by giving at least, well, the slope of its tangent, for instance, or maybe we could even go a bit a step further in its Taylor expansion. Okay, so applications of this theorem are actually quite wide. For instance, I can think of many examples. For instance, if you are producing items and you need X and Y quantities of two different materials to produce some quantity of items, right, in an engineering production. So you know that maybe for 10 items X and 20 Y, you can produce 30 Z. I don't know, something like this. That seems very easy. The production process uses 10 units of the X material plus 20 units of the Y material, and it outputs 30 items. What if now you were short on the X material, and instead of 10, you just had, well, that's not exactly local, but you just had 9. Maybe it's just not really a sum of the two. How many Ys, because you were short on X, but you have a lot of Ys in the reserves. How many Ys should you plug in so that you stay at a constant level of production? Okay, so that's the kind of answer this theorem is giving you. Well, uh, maybe not an explicit answer, but can we find this answer, and can we have at least an approximation of the value that's going to make it work? Okay, so next video we're going to cite this theorem explicitly.